Having seen the three cases of harmonic forcing, we now turn to vibration isolation. This is a design problem. We are trying to design isolators so that the vibration that is present is not converted to our device, or it is not, it is eliminated from our device. So mainly the vibration isolators are the springs and the dampers, and our aim is to determine the spring and damper values so that the vibration that is in the moving base, or let's say if there is a source of vibration, it's not transmitted to the base. So there are two cases which we will see. In both of them, we try to design the spring and the damper so that the vibration is, well, kind of minimized. So in the first problem, we have a moving base, and we want to isolate our main device, which is this mass, from the base vibration. So our objective is to isolate the motion, and to isolate the device from the source of the vibration, we want to design a vibration isolator, a spring and a damper. Examples of this is, for example, an automobile suspension system is one of those devices. Or if you have a, let's say, a delicate instrument, and if you want to isolate it from the ground motion, you might want to design a table in which the vibration is not transmitted to your sensitive device. So the solution for the moving base problem, we have found it. I'll just repeat it here. The displacement transmissibility, we have found that it is equal to TR, which is in square root of 1 plus 2 zeta R squared, divided by the magnification factor, which is 1 minus R squared squared plus 2 zeta R squared. So this is something we know already. The second problem is somewhat new. We want to isolate the base of a vibrating device from the forces. For example, if you have a machine or a washing machine or some other machine, you don't want to transmit too much force to the base, the fixed base, so that those forces might cause wear, fatigue, or vibration in other parts of the building. So you want to reduce the vibration force transmitted from the machine to the base. As I said, the examples are washing machine or other kind of machines which have inherently vibration in them. And we will find that the force transmitted to the base can be analyzed in a very similar manner. The force transmitted to the base is simply the spring force and the damping force. If again the vibration is sinusoidal, force transmitted is, if you use this formula, it's if you take the derivative, you will have a combination of sine and cosine terms, which can be combined to form a sine with a phase shift. And the magnitude of that sine can be found from the magnitude of the displacements over here, which we can find as kx times real root 1 plus 2 zeta r squared. Now we know that for direct forcing, remember this famous formula, the magnification formula, we had F0 over K divided by the magnification or multiplied by the magnification. And in our case, F0 is simply Ft0. Ft0 is this quantity. So we substitute that into our equation. So we find the transmissivity, force transmissivity, as the following equation. And this is the same, exactly the same expression as the displacement transmissivity. There is no difference in terms of the equation. So we can isolate either I design isolators either for moving base displacement or fixed base force. Moving base force is another issue which we will, for the time being, ignore. The first and the third cases are exactly the same cases. We design them similarly. Now, how do we design them? If you remember, the frequency, the displacement transmissibility, or the force transmissibility has the following figure in terms of its frequency response. The crucial point is that when the damping ratio increases at the higher frequencies, the transmissivity also increases. And this is contrary to our common intuition. You assume that if you increase the damping, the transmissivity would decrease, but no, just the opposite happens. So the ideal place to reduce the transmissibility is to use higher frequencies in terms of R, and then use as little damping as possible. So we would like to be in this frequency, in the high frequency range in our system, and then use low damping ratio. And as you see here, for example, at a certain, okay, let's skip this. So we want to design vibration isolation so that the R value should be greater than √2. And as a matter of fact, to be on the safe side, we select R greater than 3. And when R is greater than 3, the effect of damping is kind of negligible as long as you have low damping. You can have some damping, but the value of damping doesn't really change the transmissibility much. So in that case, you can assume that the damping is 0. And if you assume that the damping is 0, in this equation you have, if the damping terms are cancelled, you are left with 1/1 minus R squared term in our equation. But since R is greater than 1, it becomes R squared minus 1. From which we can solve for R squared as 1 plus the transmissivity over the transmissivity from this equation. And then we define another quantity called reduction in transmissibility. So if the transmissibility is, let's say, 90%, you have 10% reduction in transmissivity. On the other hand, if transmissivity is 10%, you have 90% reduction. So you would like to have as high reduction in transmissibility as possible. Now, if you solve for R value from here, in terms of R, you get the following equation. R equals the square root of 2 minus R divided by 1 minus R. Now, since we are doing practical work here, we use omega in terms of RPM, and we use usually the static deflection in terms of mg over k, k being the spring constant of the system. M is the mass of the system, and the g is the gravity. So using this equation now, R is equal to 2 minus R divided by 1 minus R, you can write this equation as follows. N can be written in terms of omega. So N, which is in RPM, can be written as 30 over pi G times 2 minus R divided by delta static 1 minus R. And G can be, you can take the square root of 9.81 and put it outside, so you get an expression like this. Now, this equation is is a design equation actually. From here you can find, for a given value of omega, you can find delta static, and from the delta static you can find the value of k. But you can also derive a chart from it. If you take the logarithm of both sides of this equation, you get a logarithm of n is equal to, you have square root of 1 over delta static, so it is 0.5 minus 0.5 log delta static, plus log of this 2 minus r divided by 1 minus r. Now this is a curve in terms of this log of 29.9 square root of 2 minus r divided by 1 minus r is a constant term. It is a constant for a given r. For a given r, it is constant. Then this curve is a linear curve, as we see over here. So for a given r value, you can plot the static deflection with respect to the excitation frequency in RPM. So this can be a design chart. You simply find your operating frequency or speed. Let's say it's 5,000 RPM, and then you go to amount of reduction required, like let's say 90%, 5,000 and 90%. You just go there and find the point at which they intersect, and then you go down, and then you find that the static deflection value, from which you can find given the mass, you can find the k value, the spring constant that is necessary. There is an example here. Let's say that you have an old-fashioned stereo turntable with a mass of 1 kilogram, and its excitation is 3 hertz, frequency is 3 hertz. It has a rubber mount, which has a spring constant. And we want to find the stiffness of that rubber mount if the vibration is to be reduced by 80%. Okay. So we first have to find the speed in RPMs. Since you have 3 hertz, it's you multiplied by 60. So it's 180 RPMs is your speed. R is 0.80. If you go to this chart, well, you are way out of this chart because you are somewhere around here and you cannot really reach the 80%. So you have to use the formula here. N is equal to 30 over pi, etc. You substitute everything into the equation and find that the static deflection needs to be 0.16 meter or 16 centimeters, which means that the spring constants are really very, very low. Very soft springs need to be used. So the static deflection is mg over k. M is 1, g is 9.81 divided by k, from which we find that the spring constant has to be 59.2 Newton per meter, which requires a very, very soft spring.